Hey guys, welcome back to another math video. The following video will explain the basics of Euclidean geometry. This will be done by covering the 9 basic theorems and some advanced questions after that. These are theorems that you can only use if you know what the center of a circle is. They include Theorem 1, Theorem 2 and 3, and Theorem 7. To use any of these theorems, you must know that O is the center of a circle or have the requirements to prove that O is the center of a circle. So I'm just going to briefly explain Theorem 1. In Theorem 1, when there's a line drawn from the center of a circle to a chord and the two lines are perpendicular to each other, then the chord is bisected. If there is a line drawn from the midpoint of a chord to the center of a circle, then the two lines are perpendicular to each other. This is Theorem 1. Theorem 7 is kind of similar, where if a line is drawn from the point where a tangent touches a circle to the center of the circle, then the two lines will be perpendicular. The converse of this is basically if you get two lines and they give you the angle in between, which is 90 degrees, you can use that to prove that the tangent is a tangent. Now Theorem 2 is a really important one to remember, mainly because there are so many ways they can ask you this. For Theorem 2, the angle at the center of a circle is 2 times the angle at the circumference. There are 5 examples of this. So the first thing to remember is that lines drawn from the circumference of the circle to the center of the circle are radii, and that they are all equal in length. With sketch 3, the center may not always be given, and sometimes you may be given the diameter instead. This is all you need to use sketch 3. For sketch 4 and 5, it's important to remember that these are not cyclic quads. Okay, to conclude, when you are given the center of a circle, there are a total of 7 sketches that you can use, that you may see, and 4 theorems at your disposal. Instead of looking at the question and just pondering what you could do, it might help to quickly draw these sketches on the side of your page and go through each of them one by one and see if you can actually use it in the question you are working with.
I've been a nasty girl, nasty. I've been a nasty girl, nasty.
You can only use these theorems when 4 points of a quad lie on the circumference of a circle. None of these theorems use the center of a circle. They include Theorem 5, Theorem 6, and Theorem 4. Theorem 5 is pretty simple. The opposite angles of a cyclic quad are supplementary. The converse of this would be if they would give you a quad, and if the opposite angles add up to 180, you know that the quad is cyclic. For Theorem 6, the exterior angle of a cyclic quad is equal to the interior opposite angle. The converse of this would be if they give you a quad and the exterior angle is equal to the interior opposite angle, then you know the quad would be cyclic. In Theorem 4, we only use the converse of it when we deal with cyclic quads. In Theorem 4, angles that subtend the same chord, arc, or segment will be equal, and chords that subtend the same angle will also be equal. So in conclusion, using the converse of each of these theorems, you can prove that quads are cyclic.
We outta here, baby. We outta here, baby. We outta here, baby.
Lastly, we have the tangent theorems, theorems 8 and 9. A tangent is required to use this equation, but the center or a cyclic quad is not. Theorem 8 happens outside the circle, so it's pretty easy to spot. Tangents drawn from the same point are equal in length. If there is a triangle formed between these two tangents, it's important to remember that this will make an isosceles triangle. Theorem 9 is trickier. If a triangle inside the circle touches the tangent, then the angle between the tangent and the chord is equivalent to the angle that the chord subtends. In the converse, the angles should be given to you, and you can use this to prove that the point on the circle is a tangent. So in Euclidean geometry, if they tell you that O is the center of a circle, you should already be thinking about 7 special sketches in your head. and if they tell you that there is a tangent, then you should have 2 sketches in your head. If you aren't given the center of a circle and you don't see any tangents, but you see a lot of triangles inside the circle, you're likely working with cyclic quads and angles in the same segment. When this happens, make sure you pay attention to the co-interior angles of a cyclic quad, the exterior angles of cyclic quads and triangles, as well as triangles drawn from the same arc, chord, or segment. With that out of the way, let's look at some exam type problems. Let's begin with this question. For 8 marks, find the value of x. Feel free to pause the video and attempt it yourself. Alright, let's start by filling in all the angles we can already solve for. W1 to W4 are all 90 degrees because of midpoint of chord to center of a circle. Angle ERZ is equal to 180 minus x because opposite angles in a cyclic quad. Angle O2 is 180 minus x, angles in a straight line. Because O2 is 180, Z2 will be 180 minus x over 2, angles at center 2 times angle at circumference. Now, using all of these angles, let's use angles in a triangle WRZ to find for x. 180 equals 90 plus 180 minus x plus 180 minus x over 2. This simplifies into negative 360 equals negative 3x. X equals 120. Wow, that was a mouthful. Let's consider an easier and more realistic question. This is the end of the video. Hopefully it helped you understand Euclidean a bit more.